We now introduce the design procedure of digital circuits. Some typical steps which are followed for designing a digital circuit are so number one is the specification or the requirements. These are provided by the user to the designer. Then, so what designer does do here is that designer does the input output mapping. This means that finding the corresponding output for each instance of input. Then it is optimized and designed. The circuit is optimized and designed. Optimization means if we can design a circuit by using 10 gates, then so we shouldn't be using 20 gates for designing the same function. The fourth step is then it's implemented. The circuit is implemented by using the real gates, and finally it is tested if it is working properly or not. So there are two types of digital circuits that we study in this class. So the digital circuits are of two types. The first type is combinational circuit, and the second type is sequential circuit. Combinational circuits are simple, which we already talked in the previous lectures. It's the combinational circuit. It has some input and corresponding output. Means that for every combination of input there is a corresponding output. That's why these circuits are called combinational circuits. Some typical combinational circuits that we'll study are adder, subtractor, decoder, encoder, and multiplexer. So on the other hand, sequential, this name sequential, it comes from sequence. So for example, if we want to evaluate it by 1 plus 2 plus 3 plus up to 100, so we need to perform this operation. So there are actually 99 additions. So now if we want to design such a circuit or such a process, then we need 99 adders, the 99 combinational circuits. Instead, so what we can do, so we can use a single adder, but the single adder, the same adder, we are going to use 99 times. This is the principle of the sequential design. And a typical block of the sequential designs are, so it has the combinational part, it has the combinational block, and it has input, it has output, and it has the memory elements. Some states are stored in the memory elements, and the stored states act as an input to the next operation. This is called the present state. Present state. That's next state. So when we study sequential circuits, we start with latches, and the latches are the fundamental components of the memory elements. So we'll start with latches. Then latches have some limitations, and so we study flip-flops. Flip-flops are made of latches. Then we study how to design any sequential circuit. Then we study counter and also the registers. So let's start with the adder circuits. So here the adder circuits. We want to start with the adder circuits. Adder circuits add two numbers. So in this case, we consider the binary numbers. So how we write the decimal numbers, the numbers that we use every day. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10, 11, 12. That's how we continue. So we have here 10 digits, but in binary number system we have two digits, 0 and 1, two digits. So what do we do? So we first start with 0, 1, then after 0 we don't have any digit. So now we put here 1, this 1, then 1 0 1 1, then we put here 1 0 0 1 0 1, then we put here again 1 1 0 1 1 1. So that's how we continue, and we can continue up to infinite. So we want to design circuits which can add binary numbers, and there are two types of adders. The first type is the half adder. Adds 2 bits. On the other hand, the full adder circuit adds 3 bits. So in this case, so 1 bit comes from as a previous carry from the previous operation. Let's start with the half adder circuits. Different combinations that we need to consider. So it's possible that we need to add 0 and 0, we need to add 0 and 1, we need to add 1 and 0, or we need to add 1 and 1. So now so if we add 0 and 0, then what do we get? So 0 plus 0, it gives us 0. Okay, and 0 plus 1, it gives us 1. Then 1 plus 0, it gives us 1. Then what is 1 plus 1? There you go. So 1. So we have 1. Then if we add another 1 with this 1, then we get 1 0. So here we consider this 0 as sum, and that 1 is the carry. And for this previous edition, so we had the sum, but we did not have the carry, but still we had the carry, and those carries are 0. So now if we consider the carry is the C, and S is for sum, C and S, and this one is the variable X, and the second one is the variable Y. Then we can find the truth table as, so we have two inputs, X, Y. We have sum, we have carry. So 0 0 0 1 1 0 1 1. So for 0 0 sum is 0, carry is 0. For 0 1 sum is 1, carry is 0. For 1 0 sum is 1, carry is 0. For 1 1 sum is 0 and carry is 1. Okay, so we got the truth table. Now it's easy to design the circuit. We need to find two functions, one for S and another for carry, then draw the circuit according to the functions. Okay, so for S, so we need a truth table of two variables only, X, Y, two variables, and this is for S. So for S we have 0 0 1 1 0. So 0 1 1 0, and we want to find the maximum number of ones which are consecutive and symmetric. So in this case we need to consider each of the ones individually. So we get here X Y prime plus, for that one we get X prime Y. This actually gives us an exclusive OR. So now for the KD part, so we need another truth table. And that's 0 0 0 1. So 0 0 0 1. So now the equation for KD, this would be X Y. Now let's draw the circuit. So we have two inputs and two outputs. Two inputs are X and Y. It's two inputs, and two outputs are S and C. So S is X exclusive or Y. So exclusive or, one comes from X, another comes from Y. And C, one for X and another for Y. So that's the half adder circuit. So in order to design a half adder circuit, so we need an exclusive OR gate and we need an AND gate. Let's move to the full adder circuit. So in full adder, we consider that there might be a carry from the previous operation. So let's consider we have three variables in this case, X, Y, Z. Let's consider X. X is the previous carry. X is the previous carry. Then can be 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, and we want to add them. Well, so adding 0 0 and 0 will give us 0 and 0. 0 is the sum and 0 is the carry. Now 0 0 1 will give us 1 0. So the addition on 0. So now 1 and 1. So if we add here 1 and 1, then it will give us 1 0. Again 1 1 0. One plus 1 gives us 1 0. So now we add 3 ones, 1 plus 1 plus 1. So 1 plus 1, 1 1 1. This 3 1 we need to add. Let's add these two ones first, then 1 1. So 1 1 gives us 1 0. So then we need to add 1 0 plus 1. So 1 0 plus 1 gives us 1 1. So that's actually 1 1, the result. So now we can so find the truth table. And how do we do that? How do we write the truth table? So now we have 3 inputs, x, y, z, and the 2 outputs, sum and carry. So there will be 8 combinations. Zero, 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 1, 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So for sum we have 0 1 0 1 1 0 0 1 1 0. Then we have 1 0 0 1 1 0 0 1. And for carry we have 0 0 0 1 then 0 1 1 1. Okay, so we got the truth table, and now we want to find the equations by using K-map. So we need 3 variable K-maps, one for S and another for C. Let's do first for S. This K-map is for S, and one side we have X and another side we have Y, Z. So 0 1 0 0 1 1 1 1 0, and we have another K-map here, and that K-map is for C, X Y Z 0 1 0 0 0 1 1 1 1 0. So for S we have 0 1 1 0, so 0 1 1 0. Then we have 1 0 0 1 1 0 0 1. For C we have 0 0 0 1 0 0 0 1 0 1 1 1 0 1 1 1. Okay, so then we don't need the truth table anymore. So now what do we do in this case? So we need to consider each of the ones. Let's do it for this guy. It will give us x y prime z prime plus that guy x y z plus x prime y prime z plus x prime y z prime. Now between the first two terms we can take x, then it will give us x prime z prime plus yz, plus between the third and fourth term we can take x prime, and this will give us x y prime z plus y z prime x. So this actually exclusive NOR, so y z, so we have an exclusive NOR, then plus x prime, that one is exclusive OR, so y z. So we can write x this prime and x prime this. So this is another exclusive OR. Okay, so that's so we can keep bracket here or bracket there, doesn't matter, bracket. Okay, so we can give bracket or we cannot give bracket, both are okay. And then now for C, so what do we have? So we got it for S, and I think so we don't need that anymore. We got the equation for S. Now we need to find the equation for C. So let's consider these two ones, and these two ones will give us xz, and those two ones will give us xy, and those two ones will give us yz. So xy plus xz plus yz. We try to simplify it in some way, and we write xy. Okay, we have xy now. So here y is missing, so we can write it x y plus y prime z, plus x is missing there, so we can write x plus x prime times y z. So we have xy plus xy z plus xy prime z plus xy z plus x prime y z. So we have 2xyz. So xyz plus xyz gives us xyz. So we get xy, we get that one, plus xyz plus xy prime z plus x prime yz. So if we take xy, then we get 1 plus z from these two terms, plus if we take z, then we get xy prime plus x prime y z. Now we get C equals, we know there's 1 plus z equals 1, so we have only xy here, and on the other side xy prime plus x prime y, it gives us exclusive OR. And we have the z there. These two equations now we want to implement. We have the three inputs x, y, z. So let's consider here. So we have three input x, y, and z. So first is x, y, z. First we need an exclusive OR between x and y. So we got exclusive OR between x and y. We have that one. Then another exclusive OR between x, y, and z. So another exclusive OR is between x, y, and z. And this will give us the sum for S. For carry, let's find x, y first. So we need an AND gate, and the first input is x, the second input is y. Then for the second term, so we need another AND gate. the first input is the x exclusive or y, and the second input is z. So now we need an OR gate for this plus operation. So let's consider the OR gate is here, and it has two input, the first input and the second input, and this will give us C. So we have been able to draw the full adder circuit. But now, so if we try to analyze this circuit, then we'll find that there are two half adder circuit in this circuit. The first half adder is a half adder. If you can remember the half adder circuit, then this is a half adder actually, and that is another half adder. So now if we have two half adders and one OR gate, then we can implement a full adder circuit by using two half adders and one OR gate. So now how do we perform real additions of binary numbers? Let's consider we have binary numbers like 1 0 1 1, one binary number, then 1 1 0 1, another binary number. Then so how do we add them? So 1 and 1 will give us 0 but also a carry. Then 1 and 1 will give us 0 but also a carry. 1 and 1 will give us 0 but also a carry. And 1 1 1 will give us 1 and a carry 1. So after so we do not have any carry there, initially no carry. So in order to perform this addition, so we need one half adder, because for the first operation, for the first addition, there is never a carry. Then 1 2 3 full adder circuits. So now so how can we actually figure out this? So if we have a full adder circuit and another full adder circuit, actually another full adder, or the first, if the first adder is half adder, that is also okay. And we know that so for each of the full adder there are three inputs. The two inputs are the actual numbers, and another input is the carry. So now this full adder has a carry, the previous carry. Let's consider this is C0 for carry, and input, consider X0, X1 or Y0. Okay, so X0, Y0. Then inputs X1 Y1, X2 Y2, X3 Y3, and also the carry from the previous adder circuits. And let's consider this is carry 1, carry 2, carry 3. So the first full adder has three inputs, the previous carry and two inputs, and also two outputs. The one is the sum. Let's consider this is S1 or S0, S1, S0 doesn't matter actually. Okay, so it's the sum. Then it's S1, S2, S3. So now, so when we need to add two binary numbers of 4 bits, then so we input these binary numbers. One binary number will be X0, X1, X2, X3. Another binary number will be Y0, y1, y2, y3. So we now study subtractor circuits. There are two types of subtractors again. It's half subtractor and full subtractor. So what half subtractor does, it subtract a bit from another bit. From another bit. And the full subtractor does the same thing, but it also considers a previous borrow. Okay, let's study the half subtractor first. The half subtractor. 0, 0, 0, 1, 1, 0, 1, 1. Okay, so these are the, so we need to subtract. Let's consider this one is x and that one is y. So now the question is, how do we subtract two numbers? So let's consider, we need to subtract 5 from 9. Then we find the difference between 5 and 9. So if we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that's how we go. So what is the difference between 9 and 5? Okay, so we have 5 there. So in order to reach 9 from 5, so how many counts we need to do? 1, 2, 3, 4. So the difference is 4. So then, since 9 is a larger number than 5, the borrow is 0 in this case. We don't write 0, or sometimes we write, doesn't matter. So now if we need to subtract probably 4, 6, we need to subtract 6 from 4. Then we find the difference, first difference between 4 and 6. Then how many times we need to count in order to going from 4 to 6? 4, 5, 6, 2 times. So 2 is the difference. And now, so 6 is a larger number than 4. So we have a borrow. We have a borrow. And this borrow we need to consider in the next subtraction. The same way we do, if we have number, let's consider 62 and 39. Okay, so we need to subtract. Then what do we do? So now we consider that there is a borrow. So there is a borrow here because 2 is a smaller number than 9. So if we have a borrow, then this 2 will actually be, we will add 1 here, then it will be 12. So now the difference between 9 and 12 is 3. Now we consider the borrow here. The previous borrow we add with a 3, then it will give us 4. Difference between 4 and 6 is 2. And now we don't have any borrow. Okay, that's the principle of the subtraction, and we follow the same principle in case of binary subtractions. The binary numbers we write 0, 1, 1, 0, 1, 1. Okay, so now the difference here for the first option, the difference is 0. The borrow is also 0. Now the difference. So since 0 is a smaller number than 1, so we add a borrow here. We add a borrow here. Then after adding borrow, so what do we do for this case? So after adding, so 0, 1. Then we add a borrow here, 1. Now the difference between 1, 0 and 1, the difference is 1. We had a borrow. So similarly, difference is 1, no borrow. Difference is 0, borrow is also 0. That's how we do the subtractions. Now let's find the truth table for this. So we have two inputs x, y, and two outputs. Is the borrow for B, and there's difference for D. So now we have difference, we have borrow. For difference, we have 0, 1, 1, 0. 0, 1, 1, 0. For borrow, 0, 1, 0, 0. 0, 1, 0, 0. Okay, so we got the truth table now. Now we need to find the functions by using K-maps. So we need two K-maps, one for D, another for B, and each of the K-maps, each of two variables, x, y, 0, 1, 0, 1, 0, 1, 0, 1. So for D, so what do we have? For B, what do we have? For D, we have 0, 1, 1, 0. So 0, 1, 1, 0. And for B, we have 0, 1, 0, 0. 0, 1, 0, 0. We don't need the truth table anymore. Now, what is the function for D? So we need to consider each of the one individually. So x, y prime plus for that one x prime y. This is actually an exclusive OR between x and y. And that one, it gives us x prime y, a single one. Now we want to draw the circuit, the half subtractor circuit. We have two inputs, x and y, and we have two outputs, D and B. D for difference and B for borrow. So we have exclusive OR. And for B, so we need x prime. So let's consider that we have an inverter here, x prime y. So we need an AND gate. And the second one, the second input is the y. So this is a circuit for a half subtractor. Remember this circuit, and we'll see later that we can design a full subtractor circuit by using two half subtractor circuits and an OR gate. Now we study the full subtractor. So in the full subtractor, we consider that we have a previous borrow. So let's consider x is a previous borrow. Considering this previous borrow, we want to subtract z from y. So now we'll have 8 combinations in this case: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. One, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So now, so what do we do? So by using the previous borrow, the previous borrow for the first combination is 0. So we add 0 with that 0, and 0 plus 0 gives us 0, and 0 and 0. So difference is 0. The borrow is also 0. In this case, this we add 0 with 1. Then actually 0 plus 1 gives us 1. Now actual subtraction is this. So now we got a borrow here, and the difference is also 1. So difference is 1, borrow is 0. difference is 0, borrow is also 0. Now, so what do we have? So we have the previous borrow. So we have 1 0 0. So this 1 is added with 0. So now then we have 0 1. Now the difference is 1, and the borrow is also 1. Difference is 1, and borrow is also 1. Now, so then what do we do? So we have 1 0 1. So this combination. So and for this combination, so what do we do? So we add 1 with that 1. So 1 plus 1 gives us 1 0. So 0 1 0. This is what we need to perform. So then so since the upper number is smaller than the lower number, then we add borrow here. Okay, so we got the borrow, and then the difference is now 0. So now it is 1 0. In that case it will be 0 0. In that case, okay, 1 1 1. So if we have 1 1 1, okay, so then we add this 1 and that 1, and 1 plus 1 gives us 1 0, and we have that one. So now we have a borrow here. Borrow, the difference is 1. So this is 1 1. So we got it for each of the combination. Now we find the truth table, and so now designing the circuit is easy. So what will be the truth table? The first one is the borrow for B, and the second one is the difference for D. So the truth table will be X, Y, Z. We have difference, we have borrow. So there are 8 combinations. Zero 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 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So difference is 0 1 1 0. Then 1 0 0 1 1 0 0 1, and the borrow is 0 1 0 0. 1 1 0 1. Okay, so we got the truth table. Now we need space, and let's design the circuit now. Okay, so now for that, so we need the K-map. X, Y, Z. So for difference, so we get here 0 1 0 1 1 0 0 1 1 0 1 0 0 1 1 0 0 1. Okay, so it gives us X, Y prime, Z prime plus that one, X, Y, Z plus X prime, Y prime, Z plus X prime, Y, Z prime. For the first two terms, so we have X, Y, Z, and then we have X prime, Y, Z. Actually, we find X exclusive or Y exclusive or Z. So we can put a bracket here if we want. So this is the equation for difference. Now we need to find the equation for borrow. Equation for difference. Now for borrow, let's try. Zero one zero zero 0100 1101 1101. Okay, so now for borrow B, we got x y prime plus we get x z plus we get y prime z. Now x y prime plus y is missing here, so we'll get x y z plus x y prime z plus x is missing there, so we'll get x y prime z plus x prime y prime z. So now we have x prime z twice x y prime z, so then we get x y prime plus x y prime z plus between these two terms we have z common, and then we'll also get exclusive NOR between x and y. Z is common. So now, so what do we have here? So between these two terms, x y prime is common, then we get 1 plus z. So this will actually give us x y prime plus x exclusive NOR and z. Okay, so this is the equation for borrow for B. So now we want to draw the circuit. So we don't need that truth table anymore. Okay. So we have 3 inputs, x, y, z. And 2 outputs, difference and borrow. The difference is EG. So we need an exclusive OR gate between x and y, then another exclusive OR gate between x, y and z, and this will give us the difference D. Now, so what can we do for borrow? So let's implement the AND gate, the first term first, x y prime. So we need an inverter for y prime, then an AND gate. It's x y prime, so we got y prime and then x. We got x y prime. Then we want to implement the second term, so we need an inverter. And this will give us x exclusive NOR between x and y. Then we have the z, so we need an AND gate, first input and the second input. So you got 2 terms, the first term and the second term. Then we need an OR gate. That's the borrow. Now, as I already talked that there should be 2 subtractors, 2 half subtractors in this circuit. The first half subtractor, the second half subtractor, and an OR gate. So the conclusion is that we can implement a full subtractor circuit by using 2 half subtractors and one OR gate. Thank you.